Here in this video, we would like to talk about velocity of the sound in air. There are two formulas. First one is Newton's formula, and then it is being corrected by another scientist called Laplace formula. So, before going to that, let me tell you that the flow of the air in medium broadly depends on two characters of that medium, that is, the elastic nature of the medium and the density of the medium. So it is being identified as velocity in the medium is under the square root of bulk modulus of that medium by density of the medium. So where B is being called as bulk modulus, rho is the density of the medium, is a basic kind of understanding. Further, we can continue our discussion further, or we can write our extension by saying something like Newton proposed that flow of the sound in a medium happens in a isothermal process. What do you mean by isothermal process? The temperature of the system remains constant, or change in the temperature is equal to 0. As the temperature is constant, Boyle's law in that medium P into V is constant is valid. We know at constant temperature for a given gas, pressure is inversely proportional to volume. If I differentiate this, I will get P dV plus V dP equal to 0. This is differentiation of UV formula. U V dash, that's differentiation of V, and V differentiation of U. Differentiation of a constant equal to 0. Then P dV equal to minus V dP. P can be written like minus V dP by dV. So this can be written like minus change in the pressure by change in the volume to original volume. This is the very definition of the bulk modulus itself. Bulk modulus is the bulk stress by bulk strain. Bulk stress is nothing but pressure or change in pressure. Bulk strain is change in volume by original volume. So we found bulk modulus in this case is pressure itself. So if I apply that in this relation, I will get the velocity of the sound formula as root of pressure by density. Now, this all is being proposed by Newton itself. If you apply a normal atmospheric pressure, 1.01 into 10 power 5 Pascal as a pressure, and density as the density of the air, we found that value is approximately 28 meter per second. What is that we have found? Velocity of sound in air. But this is not practically correct. Velocity of the sound is more than that. Means what? There is something wrong in the assumption that was being made here. That was being later, that is later corrected by a scientist called Laplace. That's called Laplace correction. So what Laplace said is, the flow of the air, velocity of the sound, is not going to happen in an isothermal way. Though the is not isothermal, though the given heat is constant, the compressions and rarefactions happens in the air in a very quick way, such that the temperature cannot remain constant. Flow is not isothermal means temperature is not constant, there is a change in temperature. Rather, the total heat of the system is constant. So the flow happens in a way called adiabatic process. So in adiabatic process, we have proved in heat that PV power gamma is constant, not PV constant, but PV power gamma is constant, where gamma is the ratio of specific heats. If I differentiate this further, differentiation of UV formula, like I said, U into differentiation of V, differentiation of x power n equal to n into x power n minus 1 is the formula. So differentiation of v power gamma is gamma into v power gamma minus 1. We are differentiating with respect to v, so I will write dv plus v power gamma, that is this one, into differentiation of p equal to differentiation of a constant equal to 0. So if I rearrange the terms, p gamma v power gamma minus 1 dv equal to minus v power gamma dp. So p gamma is equal to minus v power gamma dv by so okay, before going to this step, let me do one thing, right? I'll just do one simple thing. What is that simple thing I want to do is, to simplify this, let's divide this equation with v power gamma minus 1 on both sides to simplify. So p gamma v power gamma minus 1 by dv by v power gamma minus 1 equal to minus v power gamma dp by v power gamma minus 1. These two things can cancel. So what is remaining is p gamma dv equal to minus v power gamma. This goes to the numerator and the powers becomes minus gamma plus 1 and a dp. So p gamma dv equal to minus v, gamma cancels, v power 1 is remaining dp. That implies p gamma equal to minus v power 1, that is v dp by dv, that is minus r dp by dv by v minus. See, this is also change in the pressure by change in the volume to its original volume, like I said earlier, the same. So that's nothing but equal to our bulk modulus itself. So this value is nothing but bulk modulus. So here you found bulk modulus as P, but here you found it's not P, P gamma is bulk modulus. So if you substitute this value, P gamma is bulk modulus, in this core equation that we are talking about, we can found velocity of the sound as per the Laplace correction is square root of, in the place of bulk modulus, I can write gamma P by, of course, density D, where gamma is called ratio of specific heats. So if you assume sound as a monochromatic gas, its value becomes 1.4. Pressure is 1.01 into 10 power 5 Pascal. Density of the air is some value. Taking all that into consideration, if you found velocity of a sound, it's found as approximately 330 meter per second. That is perfectly matching to the practical value. So you understand the difficulty that we have. When Newton assumed the process as an isothermal process, he found velocity of sound in air as 280 meter per second, which is not coinciding with the practical value. When Laplace assumed that the process is not isothermal but adiabatic, by substituting he got a value of 330 meter per second, that is coinciding with our being acceptable range of the velocity of a sound. That's why this law is called as Newton's Laplace formula. As per Newton's and Laplace formula, velocity of a sound in air is root of gamma p by d is the conclusion that we are making here in this video. That's it. Thank you for watching. I'll see you back in the other video.